So today we will be doing some acid-base chemistry, equilibrium. What you will find out is that I will be going through some of the slides pretty fast, but I will highlight the important topics of those slides. And that's because sometimes I spend too much time deriving it when really what you need to know is just the equations to use. And so that's what I'm going to try and make sure that you guys understand. So let me go ahead and get started here, because we do have a bunch of things to catch up with. And even though we're talking about acid-base chemistry, the theme is still equilibrium. So that should help you in terms of understanding chapter 15 material. What we're talking about, of course, is proton transfer, whether the chemical is delivering it or receiving it. We're talking about acid-base chemistry. Okay, so let's take a look at this. And these are the Lewis structure as well as the geometry of how this particular phenomena occurs in terms of proton transfer and proton acceptor. What you will find out is now we're going to the Lowry-Brownsted definition of acids and base. And again, this is going to be more general in the context of acid-base chemistry. The Arrhenius definition was simply increasing hydrogen ion concentration and increasing hydroxide ion concentration. Now we're looking at proton donor, proton acceptor, and here are some examples. And we've talked about this last time, okay? What I really want to point out in this particular discussion is that in the process of transferring protons, the chemical in which the species that transfer protons to is now going to be a chemical that can accept protons. And we call these pairs conjugate pairs. So if you take a look at ammonia and hydrochloric acid, the hydrochloric acid is the acid. It's going to be the chemical that delivers the hydrogen. Okay, this hydrogen right here, and it delivers it to ammonia. In the process of getting rid of its hydrogen, the hydrochloric acid now becomes the chloride with its missing hydrogen. So we call those conjugate pairs. Conjugate just means joining with, and these are the pairs that are these are the pairs that is different by a proton. In fact, conjugate pairs are only different by one hydrogen, one proton. So HCl is a conjugate pair of Cl minus. Cl minus is a conjugate pair of HCl. Likewise, NH3 is a conjugate pair of NH4. NH4 is the conjugate pair of NH3. Okay, you should be able to recognize between HCl and NH3 which is the base and which is the acid. Likewise, if the reaction were going to go in the reverse direction, this reaction does not go in the reverse direction, by the way, okay? And you'll see why. But if it were to go in the reverse direction, then NH4 plus would be the chemical that delivers the hydrogen to chloride, and chloride would be the chemical that accepts the hydrogen. So in this particular case, in the reverse direction, NH4 plus is the acid, Cl minus is the base. Now you might ask, well, why doesn't the reaction occur in the reverse direction? And the reason why it doesn't occur in the reverse direction is because the hydrochloric acid is a strong acid, okay? And if it's a strong acid, it doesn't want to form HCl again, okay? HCl wants to get rid of its hydrogen. If there's a chemical that is going to be available to accept the hydrogen, it doesn't want to form HCl. By definition, HCl wants to dissociate 100%. So if there's the hydrogen available, Cl minus is not going to take it back. Okay, Cl minus is not going to take it back. It's a one-way street. So make sure you recognize conjugate pairs, and make sure you recognize which is the conjugate acid and which is the conjugate base. And there's a whole bunch of examples in the next few slides that gives you examples of that. Here's bicarbonate and water. In this particular case, bicarbonate has a hydrogen to deliver. And so it's going to deliver its hydrogen to water, and water becomes hydronium ion in the process of picking up that hydrogen. So bicarbonate, HCO3, is the acid, water is the base. In the reverse direction, however, and this reaction will go in the reverse direction. Why? Because HCO3 is a weak acid. It's not one of our 7 strong acid. In the reverse direction, H3O plus will deliver its hydrogen to carbonate ion, and in the process becomes water. So it's an equilibrium process. So we can say that bicarbonate, HCO3, is the acid, CO3 minus 2 is the base, and those are conjugate pairs, okay? And you can see that right here. You can see that right here in terms of, that, okay? So what we have in this particular case is, again, there's always going to be a conjugate pair on the left and a conjugate pair on the right. Likewise here, you have conjugate pairs right there between the acids and the base. Okay. HCl3 plus 3 minus and HS. The chemical that delivers the hydrogen is going to be HCl3 minus, and it becomes CO3 minus 2. The chemical that accepts the hydrogen is HS minus, so that's the base, and becomes H2S. In the reverse direction, however, H2S is the chemical that delivers the hydrogen to CO3, so that's the acid. Again, it's the conjugate pairs, okay? And here are more examples. And you might ask yourself, well, yeah, conjugate pairs are pretty straightforward. Why do we need to know them? You need to know them because what happens is that when you have an acid and it converts over to its conjugate pair, then the conjugate pair in the chemistry is the anti-original chemical. The acid becomes the base, okay, between the conjugate pairs. So an acid will always have a conjugate pair that is a base. And then if it's a somewhat strong acid, okay, somewhat strong weak acid, then the base is somewhat of a strong base, okay? It becomes its opposite. A weak acid will become a strong base. Weak base will become a strong acid. It becomes its anti-self. And you see that in relations to its Ka, okay? So I just wanna make you aware of that. So here are more chemicals. And the question here is, what are the conjugate pairs of NH3, IO minus? This is the acetate ion. This is the bi-acid arsenate. Remember, PO4 minus 3 is phosphate. So AsO4 minus 3 is arsenate. It's in the same family. And AsO4, now it's minus 2, is biarsenate. Just like PO4 minus 2 is biphosphate. So again, you don't have to memorize these chemicals just because you haven't seen it before. Recognize the family that it comes from and remember that pattern. So what are the conjugate pairs? Of course, that's going to be the conjugate pair here. That's going to be the conjugate pair here. That's a conjugate pair. And this has 2 conjugate pair. Could be this or this right here. Okay, but H2 ASO4 is not a conjugate pair of ASO4 minus 3. Those are not conjugate pairs. And the reason why those are not conjugate pairs is because they differ by more than 1 hydrogen. Conjugate pairs always differ only by 1 hydrogen, and you can recognize that. Anyway, these are just more examples of that. Okay. So if you take a look at this right here, you see that these are strong acids over here. These are strong acids over here, and that's its conjugate pair. These are weak acid or almost bases at the bottom. Let's go over here. These are weak acids, and that's its conjugate pair. If you look at this series, however, what you will recognize is those are the chemicals that are great proton acceptors. And indeed, what happens is that the conjugate pairs of weak acids have bases that are somewhat strong. If a chemical is unwilling to give up its hydrogen, like in HCO3 minus, or not unwilling, but has a hard time giving up its hydrogen, then don't you think that it prefers to keep its hydrogen? And by definition, a chemical that is attracted to the hydrogen is a somewhat strong base. So remember the definition of an acid and a base, the Bronsted-Lowry definition. An acid is a chemical that wants to give up its hydrogen really efficiently. Okay, the more willing it's going to give up its hydrogen, the more stronger that acid is. A base is a chemical that wants to accept a hydrogen. Okay, it's a proton acceptor. The more willing it's going to accept the hydrogen, the stronger the base. So if you've got a chemical that is unwilling to give up its hydrogen, then the chemical without that hydrogen is going to be a chemical that really wants to attract that hydrogen, like these pairs right here. HCO3 minus is not a very good proton donor. On the other hand, CO3 minus 2 is a very good proton acceptor. It's still a weak base, but it's going to be a stronger weak base among these series here. So again, what I'm trying to illustrate here is that in between the conjugate pairs, if you have a strong weak acid, okay, what I mean by strong weak acid, it's not one of our 7 strong acid, but if you have a strong weak acid, then its conjugate is going to be a weak base, okay? It's going to be opposite of that. Its conjugate is going to have an opposite. And what you will find out is that there's going to be a Ka and a Kb that you can get used to gauge the ability for that chemical to give up its hydrogen and the ability for that chemical to accept a hydrogen. What you will see is that there is an inverse relationship between the Ka and the Kb. If the Ka is large, then the Kb is small. If the Kb is large, then the Ka is small. So there's a direct inverse relationship between the two. That's why it becomes its opposite. And you'll see that. So here's a more extensive list. Here's a more extensive list. And so here, what we have, I remind you again that strong acids will dissociate 100%, and they will give you stoichiometric amount of hydrogen ion if you have that chemical in aqueous solution. It's 100%. If you've got a dibasic chemical, then it'll give you twice as much hydroxide in solution when it dissolves. So these are just examples. If you got, again, remember your 7 strong acids. Why? Because you don't have to work very hard to figure out what the pH value is, to figure out what the hydronium ion value is. If you've got a 0.001 molar perchloric acid, then your hydrogen ion is also 0.0010 molar. Okay, that's just by definition because it's a strong acid. So the question that generally occurs is, then what is the pH of the solution? If you've got a 0.0010 molar perchloric acid, your hydrogen ion is also 0.0010 molar. And so if you take the negative log of 1.0 times 10 to the minus 3, that pH is just equals to 3. Okay. Likewise with the base. If you have a base that is 0.001 molar, look at the chemistry. Okay, your hydroxide is not 0.001 molar. If it was sodium hydroxide, yes, you have calcium hydroxide here. So it's going to be a 1:2 ratio. Your hydroxide ion concentration is 0.0020 molar. And if you want to know what the pH is, first figure out what the pOH is. The pOH is negative log of the hydroxide ion concentration. Plug that in there. And then remember that we're assuming now 25 degrees, pure water, that pH plus pOH equals 14. Okay, so you can do this off the top of your head. You don't need to do any equilibrium analysis. So this is what we have right here. What we have is, sorry, for some reason, my iPad will not erase, okay? So I apologize for that. Anyway, if you take a look at this right here, what you will see is that the concentration of the hydroxide is going to be 0.0020. And if you take the negative log of that, that's 2.70. And if you subtract 14 from 2.0, your pH is 11.3. Please remember that as well, that when you have hydroxide and you're asked to calculate the pH, then you can calculate the pH in one of two ways. You can, like we talked about in last discussion, you can use this equation, or you can use this equation. Assuming it's 25 degrees. So what you can do is you can take 0.002, plug it in here. You know what the Kw is. Solve for the hydronium ion concentration. And then from the hydronium ion concentration, you can calculate the pH. So there's multiple ways of getting the pH from the base information, in other words. So again, a reminder that strong acid, strong base are strong electrolytes. Okay, weak acid, weak base are weak electrolytes, and so you have to go through the equilibrium. You have to go through the equilibrium like you see right here. And when you have to go through the equilibrium, you need to do the ice table. What I will do here is I will show you the fundamentals of why you need to go through the ice table, but then I will show you a shortcut that will always work provided certain conditions apply. Okay, I teach analytical chemistry, which is the quantitative analysis of chemicals. It's like what we did in the second part of chapter 17. Okay, where you're trying to figure out not only the identity of chemicals in a test tube probably, but also know the amount. Anyway, we cover somewhere along of 20 chapters, maybe 21 chapters in one semester. And so we cover acid-base chemistry in like about a week and a half. Okay, all of the stuff that we're doing right here. And in order to do that amount of information, we have to do some shortcuts. And I will share with you some of the shortcuts that you can apply in acid-base chemistry. And why can we do some of these shortcuts? Because in acid-base chemistry, the reaction that occurs always occurs with one hydrogen being released from a chemical. It's never multiple hydrogens. And so the analysis that you do is always a hydrogen and its conjugate, one at a time, even for polyprotic systems. Albeit polyprotic system, you have to treat 3 problems or 2 problems. It's still simplistic in the analysis. Okay, so that's what I'm going to try and share with you today, is some of the shortcuts that you can apply in some of these problems. Anyway, we're going to deal with equilibrium. And because we're dealing with equilibrium, we have to deal with equilibrium constants. And these are some of the chemicals that have equilibrium constants, because why? They are weak acids. They are weak acids. Okay, so when you solve equilibrium problems, remember some of the fundamentals. Make sure that the chemical formulas in your reactions are sound. Make sure they are correct, because if they are not correct, you're already starting off. You probably get the wrong answer. Okay, make sure you balance it. Make sure you are able to determine the mass action expression, construct an I stable, define X. X is the amount of chemical in which the acid dissociates to. Use simplifying assumptions if it's valid. Okay, use simplifying assumptions if it's valid. And remember this rule right here. If you take the initial concentration and you divide it by the K equilibrium, and it's greater than 400, then you're probably going to need to do, then simplifying assumptions is going to be valid, okay? If it's less than 400, then you're going to have to do a second iteration or quadratic. And we talked about this last time. So this is how you can do real quickly a validation as to whether simplifying assumptions work. And in most cases, acid-base chemistry, they do work. They do work. Why? Because your equilibrium constant, your Ka, is so small, it makes this number really large, much more larger than 400. Okay, so this will validate the 5% rule. And if it's less than 400 or it's less than 5%, then you need to do a second iteration. Okay. The other thing that you have to remember is that in acid-base chemistry, you always have water. And water will always auto-ionize to the tune of the hydronium ion concentration is always 1 × 10⁻⁷ in pure water at 25 degrees. So that's an initial concentration you have to think about, but not worry about in most cases. And I'll show you that. I'll show you that the reason why you could ignore it, okay? The reason why you could ignore it is because it's pretty minute. It's pretty small for most conditions. So that's this assumption right here. A weak acid has a small Ka, therefore X is very small compared to the original acid concentration. And then you can apply the assumptions to make the math easier. So let's take a look at hydrofluoric acid. Hydrofluoric acid is one of those acids. It's a halogenated acid. It's one of those acids that has the weak small Ka. Unlike hydrochloric, hydrobromic, hydroiodic, those are strong acids. Hydrofluoric acid is not a strong acid. It's a weak acid. If you've got 100 molecules of hydrofluoric acid, probably 1–2% of them, depending on the temperatures, will dissociate. Most of it stays as HF. Most of it stays as this guy right here. Okay, so this example right here tells you that most of it stays as like 3% of it ionized, 97% of it stays as HF. Here's an illustration to show that. This is a strong acid, strong situation. This is a weak acid situation. This would apply to HF. This would be an example of HF, where you've got, say, 100% weak acid. When it dissociates, very little actually goes into hydrogen ion and its conjugate. Most of it stays intact. That's, again, the concept of a weak acid, weak base. Okay, so the K equilibrium on that is going to be a small number. So we can actually do this. We can do this. That's the way to clear my screen. Okay, in terms of an I stable. Now, here's an I stable. We have HF. We have 0.010 molar. Water is constant. So that's why I put a lot there, because it never shows up in the mass action expression, although you have to write it in the reaction. Why? Because water is the chemical that accepts the hydrogen. So it's going to be the base in this reaction and becomes H3O+. And the initial concentration of H3O plus is going to be about 1 times 10 to the minus 7. Why? Because water gives you hydronium to the tune of 1 times 10 to the minus 7. Initially, HF hasn't dissociated, so you put a 0 in that initial line. During the course of the reaction, this is going to be delta change. You have minus X. There's a certain amount of HF that dissociate. Water is going to pick that up. It's going to be used up, and you get a plus X here and a plus X here. So at equilibrium, the HF concentration at equilibrium is 0.1 minus X. We don't have to worry about water because it's constant. The amount of hydronium that forms is going to be 1 times 10 to the minus 7 plus X, and the amount of fluoride that forms is plus X as well. Now, what we're going to do here is we're going to assume that 1 times 10 to the minus 7 is so much smaller than X that we're going to ignore it, and we're just going to make this X right here. We can make that assumption because in most parts, 1 times 10 to the minus 7 is a small number, okay? So what we have here is this equation really reduces down to X squared over HF, okay? And HF is 0.10 minus X, 0.10 minus X. But look at the K equilibrium. I don't show it to you here, but it's going to be 1 times 10 to the minus 4. And so you have another assumption that you can make here, and that's that HF is approximately equal to 0.10 molar. That simplifies the math tremendously. That's why you can use the shortcut that I'm going to introduce to you in the next slide, okay? And that's equal to Ka. So we're making two assumptions. One, that X is so much bigger than 1 times 10 to the minus 7. So it simplifies this right here. But X is so much smaller than the HF concentration that it simplifies this part right here. And when you do that, the math really becomes super easy. Okay, the math really becomes super easy. So that's what you see here. This is an example where I have two acids. They're both halogenated acid. That is, it's got a hydrogen and a halogen. One of them is going to be HCl. The other one's going to be HF. They're both 0.10 molar. In the first question, what is the pH of a hydrochloric acid that's 0.10 molar? You don't even have to lift your pen, okay? You should know that 0.10 molar is 1 times 10 to the minus 1. The pH for that is just 1. Here it is right here. And why do you know that? Because you recognize HCl as a strong acid. On the other hand, if you have a weak acid, it's not that simple. It's not that simple. You have to work through the equilibrium, but I will show you a shortcut here, okay? First of all, here's the solution. What I want to show you is this right here. Ka equals 6.8 times 10 to the minus 4. Let's see if we can do simplifying assumption. The initial concentration for HF is 0.10. The Ka is 6.8 times 10 to the minus 4. Let's see what that equals to, okay? Remember, in order to validate simplifying assumption, you take your initial concentration divided by the K equilibrium. And if that is greater than 400, then your simplifying assumption applies. If it's less than 400, then simplifying assumptions will not apply. So in this particular case, 0.1 divided by 6.8 to the 4 negative, that comes out to 147, which is less than 400, which means that simplifying assumptions won't work. But I can make a simplifying assumption and then do a second iteration to make that better. And usually that's good enough, at least for our class, okay? So let me just walk you through this real quick and show you how we do the second iteration. Or if you're really a math whiz, just take the original math and do the quadratic. Simplifying assumption, you will see, is actually easier. Here we have the ice table. We have 0.10. We have in here we have water, and the reason why I leave it out is because it never really shows up in the mass action expression. It's responsible for forming H3O plus. This really is H3O plus. Okay, but what you will see is that you're going to get a mass action expression that deals with H3O plus, H plus, F minus, and HF. So this is our initial line. This is our initial line. The initial concentration of HF is 0.1. Hydrogen ion is 1 times 10 minus 7. Fluoride ion is 0. The change is minus X, plus X, plus X. And so at equilibrium, we have this right here. So we can make a few assumptions here. This is just your water. This is just your fluoride. This is just your HF. And the assumption here is that we're going to simplify this right here to X. Okay. And then we're going to simplify this right here to 0.10. Why can we do that? Because Ka is small. At least for this part, we've got to make that if we want to simplify the math. Of course, we're going to have to do a second iteration according to this right here, according to this right here, okay? But for now, just worry about solving the initial X value. So when you do this, this math is really easy. You've got 6.8 times 10 to the minus 4. This becomes X squared over 0.1. You have, bring 0.1 over to this side. Okay, that would be 6.8 times 10 to the minus 5. You take the square root of both sides. And when you take the square root of both sides, you get 8.25 times 10 to the minus 3 for your hydrogen ion concentration. And you notice that number is way bigger than 1 times 10 to the minus 7. So this assumption right here actually is valid. Okay, that assumption is valid. But this assumption over here is not so valid. If you take 0.1 and you subtract 0.008, it's not really 0.1. Okay, that number is too big. In fact, if you use the 5% rule, you see that it's 8.24%. So what can we do to improve this? What we can do is use this X value right here and make this assumption better, make that assumption better. Actually calculate 0.10 minus 0.00825, and that will be your initial that will be your HF equilibrium concentration. And then use that right here so that you can get a better value of X. That's how you do a second iteration. You use the answer from the first to make your first assumption better, okay? And when you can do that, then you can work out the math again and then solve for a better number, which is that. And again, in general, 2 iterations enough. Once you have that better number, then you can assume that your hydrogen ion concentration, and you take the negative log of that, and you can see that the negative log of 7.9 times 10 to the minus 3 is 2.10. Okay, 7.9 times 10 minus 3 is 2.10. The 5% rule on that second iteration works. And in general, I'm only going to ask you 2 iterations if you're going to do that. Okay, the rest of it is math. I want you to understand the chemistry. So for this particular problem, what you see here is that the HF has a pH of 2.10 when you have a 0.1 molar HF concentration, whereas the HCl has a concentration or a pH of 1. Quite a big difference for the same concentration, and they're both halogenated acid. Why the difference? Because one is a strong acid. The original chemical would dissociate 100%. The other is a weak acid. The original chemical will only dissociate a small fraction of a time. Okay. Now, I want to share with you a little shortcut that you can use based on the two assumptions that we did here. What were the two assumptions? The two assumptions were that the change, that is the amount of hydrogen ions that the original acid releases, that amount is much bigger than 1 times 10 to the minus 7. Okay, this assumption right here, that the amount that the weak acid gives up is going to be bigger than 1 times 10 to the minus 7. That's your first assumption. The second assumption is that the amount of hydrogen ion that is released is so much smaller compared to the original concentration that it's negligible. That's this assumption over here. Okay. Sometimes that assumption is not valid, especially if you use this criteria right here. Remember, this is the initial concentration over the K equilibrium, and that has to be greater than 400. If it's less than 400, then you need a second iteration. Quick and dirty check. But if you can do that particular, if you know about these assumptions that work, then the shortcut that I offer you is the following. And the reason why the shortcut works is because most problems will ask you, what is the pH? What is the hydrogen ion concentration? What is X? So from here, it actually comes from here. The X value, or the H3O plus value, is equal to the square root of the Ka times the original acid concentration. Okay, this is a nice equation to remember, because if you have the Ka and the original acid concentration, why the original acid concentration? Because you're assuming that not very much of it dissociate. And you take the square root of that, that'll give you your hydrogen ion concentration. Why is it the square root? Because this right here is X squared. That's X squared. So remember that shortcut. Let me write it here again. The H plus concentration, or the hydronium, is equal to the square root. The square root comes from the fact that the hydrogen ion and the fluoride ion, the hydrogen ion and the conjugate are the same amount. Why is it the same amount? Because if you've got an acid and it is dissociate to its hydrogen and its conjugate, then they form the same amount when it goes to products. That's why it's X squared. That's why it's X squared right here. So in order to just calculate X, you need the square root. Then you need the Ka, and then you need the original acid concentration. And we denote that by HA naught. Okay. If you want to calculate the base, if you have a base, then the base concentration is equal to the square root of the Kb times the original base, conjugate base concentration, whatever the initial concentration is right here. Use that shortcut. It'll save you so much time, especially when it comes to titrations. Okay. But know when that shortcut is valid right here. Know when that shortcut is valid. So let's move on. Okay, let's move on. Here are some examples again. And let me just show you that this thing really works real quickly. The chemical here is, we have phenol acetic acid, okay? And we have a pH of, we have a 0.12 molar, okay? And we want to know exactly what is the pH of that particular solution. Well, it's actually calculating the Ka. So this is not a problem that you would solve, but this problem, if you realize that the pH is 0.12, then you can, from the pH, you can get the hydronium ion concentration, right? And if you have the hydronium ion concentration, then you also have the conjugate base. This would be the H plus. Then you also have the conjugate base, which is this chemical right here, without that acid, that would be the phenyl acetate ion. And that those two are going to be the same. And then they give you the initial concentration of the chemical, 0.12. So you can plug 0.12 right here. You can calculate these values right here. They're going to be an equal amount, and then you can calculate Ka, which I think is what they do right in this particular problem. So go over it. And again, it's just to demonstrate to you that in this particular case, we use the mass action expression to solve this particular problem. Okay, you can see that's exactly what they did right here. This right here is propanoic acid. And in this particular problem, they give you a concentration of 0.10 molar propanoic acid. Let me see if our shortcut works. Okay, first of all, I know that the Ka for this particular guy is 1.3 times 10 to the minus 5. That's our Ka. If I take 0.1 and divide that by 1.3 times 10 to the minus 5, that ratio right there happens to be 7,692, way bigger than 400. I can do my simplifying assumptions here. In fact, what I'm going to do is I'm going to just go straight to this equation. H plus is equal to the square root of the Ka, 1.3 times 10 to the minus 5, okay, times 0.10. And that will be my H plus concentration. And then I can get my pH from that. Again, showing you the tricks of the trade here. If I take 1.3 times 10 to the minus 5 and multiply it by 0.1, that's 1.3 times 10 to the minus 6. So I'm going to punch that into my calculator. And then I'm going to take the square root of that. And so my hydronium ion concentration is 1.14 times 10 to the minus 3. And if I take the negative log of that, it's in my calculator. Okay, then what you find out is my pH is 2.94, which is where is the pH shown here? Okay, well, this is the answer, and I don't see the pH calculated here, but that would be the correct true answer. Okay, and you can see it works, and I didn't even have to do the ice table. But know that it originates from the ice table, okay? You can't forget the fundamentals. Why can't you forget the fundamentals? Because the shortcut's just there, and you can't just use it not knowing where it comes from. If you know the fundamentals, you can always get to the correct answer because you're using the fundamentals, the ice table, as the basis to solve that problem. Sometimes we do the shortcut without knowing where it comes from, and then we can easily make mistakes. So again, it's a nice shortcut, but remember that it comes from the ice table. It comes from the ice table. Anyway, let me move on. Okay, find the concentration, pH, and Ka given the percent dissociation. Percent dissociation, or the percent ionization, tells you what percent of the chemical actually goes and breaks apart. If you've got 100 and only 3 will dissociate, then the percent dissociation is 3%. If you've got 100 and only 7 will ionize, then the percent dissociation is 7%. That's the percent dissociation. And that's what you see right here. It's the amount that ionizes divided by the initial times 100 if we're going to get a percent. Why is that important? Because if you don't have the Ka, and you know the percent dissociation, if you know that you got 100 and only 3% of it dissociate, then you know the concentration of all the chemicals at equilibrium. You will know that originally you had 100, now you have 97 at equilibrium, 3 at hydrogen ion and 3 conjugate. So 3 squared divided by 197 will be the Ka. So you don't need the Ka to figure out the pH of the solution. If you know the percent dissociation, then you know from the original amount how much hydrogen is produced. Okay, so this is another way of solving equilibrium problems if we know the percent dissociation. But the percent dissociation, unlike equilibrium constant, is not constant. Okay, it's not constant because it's based on Le Chatelier's principle. If you've got a lot of chemicals already in solution, not very much of it's going to go and break apart. Why? Because you've already got a lot of chemicals in solution. Okay, it doesn't want to form more. In other words, if you've got a very few amount of chemicals in solution, in other words, low concentration, then in Le Chatelier's thinking, more of it will dissociate so that you get more ions out there. It goes back to the Le Chatelier's principle. And you see that when we derive the percent dissociation equation, that it's proportional to the, or inversely proportional to the concentration. Okay, inversely proportional to the concentration. So let's take a look at this right here. Let's say we have a 9.4% of an acid. What is the pH of the solution? Well, if you got a 0.200 molar and it's 9.4% dissociation, then that acid, we'll make it a general, we'll go down to this and this, and 9.4% of 0.2 is going to be 0.0188. If you want to calculate the pH, just take the negative log of that number. Just take the negative log of that number, because what is the pH? It's the hydrogen ion concentration, the log function of that. You don't need anything else. If you have the hydrogen ion concentration of that solution and you take the negative log of that, you've got the pH. Here, suppose we want to calculate the equilibrium constant. Well, you know what the equilibrium concentration of both the acid and the conjugate is. And then you know that if you've got 0.200 and you subtract 0.0188, then the equilibrium concentration of the original acid is going to be 0.0188 minus 0.1812. So you can use that information. K equilibrium is just equal to 0.0188 squared divided by 0.1812. Why? Because remember, equilibrium concentration is the mass action expression, and mass action expression is the concentration of all the chemical at equilibrium. These are the concentrations of all the chemical at equilibrium if it has a dissociation constant of 9.4. Dissociation constant tells you that how much it will dissociate to at equilibrium. So this is how you would solve for the equilibrium constant. This is how you would solve for the pH. Okay. And so you can see that giving the dissociation constant, you can get information from that. Anyway, you can see right here, these are the concentrations right here. These are the concentrations of the chemicals at equilibrium. If you subtract 0.0188 from 0.2, this is the concentration of the acid at equilibrium, and then you can just plug it in to get the equilibrium constant. So that's what I wanted to show right here. Okay, so here's the derivation. I'm not going to go through the derivation. What I do want to show you is the following. This is alpha. Okay, and this is X. But alpha tells you that the percent dissociation is directly proportional to the how much of the ions form, how much of hydrogen ion forms. That's your X. That's this right here. Okay, but it's also inversely proportional to the concentration. It's inversely proportional to concentration. So the higher the concentration, the lower the percent dissociation. The smaller the concentration, the bigger the percent dissociation. And you see that from this graph. This is high ionization. This is high concentration. This is concentration on the x-axis. You notice at high concentration, the percent decreases. A lower concentration, the percent dissociation increases. There's an inverse relationship, and it comes from this equation right here, from that equation right there. That's your alpha. The alpha is the amount of change divided by the original times 100. And the original is the concentration of the analyte before anything happens. Before anything happens. Okay. So I just want you to be aware of alpha. For those of you in lab, you guys will be introduced to alpha in the activity. Okay. Let me talk to you guys about polyprotic system. Polyprotic systems are acids that have more than one hydrogen. Remember I told you earlier today that thing about acid-base chemistry is that you only treat one math problem at a time, even if it's a polyprotic system. Why is that? The reason why that is because dissociation occurs one step at a time, at least in the way we analyze it. So if you got nitrous acid, this is a weak acid. This is not nitric acid. You guys should remember that nitric acid is HNO3. That's a strong acid. Nitrous acid is HNO2. That's a weak acid. If you have a nitrous acid and you put it in water, it's going to dissociate, and the degree of dissociation is going to depend on the Ka of that acid, which happens to be 7.1 times 10 to the minus 4. Okay. It's monoprotic. In other words, it can deliver one hydrogen at a time. Now, if you have a chemical that's diprotic, H2SO3. H2SO3, remember, is not sulfuric acid. Sulfuric acid is H2SO4. This is sulfurous acid, H2SO3. Okay, sulfurous acid. It's a weak acid, but it's a diprotic. Di meaning two, protic meaning releases two hydrogen. It's a diprotic acid. If it's a diprotic acid or a polyprotic acid, then what happens in the chemistry is that first the sulfurous acid gets rid of its hydrogen, one hydrogen only. And it does that to the tune of 1.7 times 10 to the minus 2. Okay. The conjugate of that is HSO3 minus. The H2SO3 will deliver only one hydrogen. It will not deliver two hydrogen. Okay, it will deliver one hydrogen and you get HSO3 minus. Then when you get HO3 minus build up and it needs to deliver more than when it needs to deliver a second hydrogen, then it does so using this reaction. And that happens in the tune of 6.4 times 10 to the minus 8. Notice that the second Ka, we call that Ka2, is so much smaller than Ka1. Why? Because one, you're taking a hydrogen from a negative species. Okay, that hydrogen's positive. It wants to be attracted to that negative species. It's going to be much more difficult to get rid of that hydrogen, but it can't come off. It can't come off to the tune of 6.4 times 10 to the minus 8. Because these things are treated separately, then you can do H plus is equal to Ka1 times the original concentration of your acid. You can do that. Okay. The second one needs a little bit more explanation. Needs a little bit more explanation. You'll see that in the time left. Let's take a look at a triprotic acid. This is phosphoric acid. Phosphoric acid. Remember phosphoric acid, H3PO4? Well, that's a weak triprotic acid. Don't confuse that with H3PO3. H3PO3, unlike its formula, is only diprotic. It's not a triprotic acid, okay? For those of you in lab, you're going to see why it's only a diprotic acid through its Lewis structure. But nevertheless, let's, going off on a tangent again. Phosphoric acid is a triprotic acid. The first hydrogen comes off in the tune of 7.3 times 10 to the minus 3. The second comes off at 6.2 times 10 to the minus 8. The third one is really hard. It's 4.2 times 10 to the minus 3. So you get these three reactions, and you got to treat each reaction one equation at a time. Okay, so it's tedious in that manner, but it's simple because you don't have to worry about taking the cube root or raising something to the third power. You don't have to worry about that. Everything can be solved using simplifying assumptions, especially when you look at these equilibriums. They're very small. They're very small. Okay, so again, you can use the simplifying assumptions. That's what I'm saying right here. Here are more polyprotic systems. This is oxalic acid. Oxalic acid is diprotic. This is phosphorus acid. Phosphorus acid, remember, is H3PO3. It's not H3PO4. And look, there's only 2 Kas here, which means that only 2 hydrogens can come off. Why? Look at the Lewis structure. This hydrogen can come off because it's attached to an oxygen. This hydrogen can come off because it's attached to a hydrogen. In other words, it's an acidic hydrogen. Acidic hydrogens are hydrogens that can come off and on. This hydrogen will not come off because it's not attached to an oxygen. It's attached to a phosphorus. That bond is very strong. That bond is very strong. That's not an acidic hydrogen. That's why phosphorus acid is only diprotic. You wouldn't know that from the formula, but I'm telling you right here, it's a diprotic acid. Sulfurous acid, likewise, well, there's only 2 hydrogens here. It's a diprotic. Phosphoric acid is certainly triprotic. Anyway, first hydrogen, Ka1, second hydrogen, Ka2, third hydrogen, Ka3, if there is a third hydrogen. KBs work the same way. When you add the first hydrogen to a base, that's KB1. When you add a second hydrogen to a base, that's KB2. When you add a third hydrogen to a base, that's KB3. Now you might ask, well, what chemical is that? PO4 minus 3 is a base. When it adds a first hydrogen, that's KB1, okay? And it's HPO4 minus 2. When it adds a second hydrogen, that's KB2, and it becomes H2PO4 minus, and when it adds a third hydrogen, that's KB3. Okay, so the 1, 2, and 3 indicates the sequence by which either hydrogen is released or hydrogen's added. If we go in the reverse direction, if phosphoric acid releases its hydrogen, that is Ka1, this is Ka2, and this is Ka3. Okay, so you can see that Kb1, the reverse of that is Ka3, Kb2, the reverse of that is Ka2, and Kb3, the reverse of that is Ka1. Why is that important? Because these guys right here have a special relationship that I might not get to in today's discussion, okay? But there's a special relationship between the Kas and Kbs between conjugate pairs, These two are conjugate pairs. These two are conjugate pairs. And then these two are conjugate pairs. This is not a conjugate pair of that. Okay. Sorry for the scribbling, but for some reason I can't erase. My pen doesn't work. I think I need to reboot my program here, but we're going to lose time if I do that. So you just have to deal with me. Here's a series of polyprotic acid. And in this particular case, I'm going to show you what happens to carbonic acid. And I'll show you that real quick. So carbonic acid is a diprotic acid. And so the question here is, what is the pH of carbonic acid when you have that chemical? And what are the concentrations of H2CO3, HCO3, and CO3 minus 2. Those are the type of questions that you can have for a polyprotic system. If you have a certain amount of acid, let's say I have 0.010 molar, and I put that in solution, what is the pH of that solution? What is the carbonic acid concentration? What is the bicarbonate ion concentration? What is the carbonate ion concentration? And what I'm going to show you here is that the Ka1 is just treating this first equilibrium right here. And we're going to use this equilibrium constant. And so what you can do here is the shortcut. Hydronium ion concentration is equal to the square root of the bicarbonate, initial bicarbonate concentration times the Ka1 for that. And you can get the hydrogen ion concentration. Okay, and this guy right here is equal to that guy right there because they form an equal amount. Okay, they form an equal amount. The second equilibrium right here is taking this reaction right here, okay, and then solving the mass action expression using this equilibrium constant. Let's take a look at that. I'm going to expand this a little bit because I want to reveal to you something that is really a shortcut revelation. Okay, if I do the mass action expression for that, then that's Ka2 is equal to hydronium ion concentration times carbonate ion concentration. That's just these two right here, divided by HCO3 minus. Now remember, this amount right here is going to be a number from the first equilibrium. It's going to be a number from the first equilibrium because when the first equilibrium produces hydronium, you got to use that concentration for the second equilibrium because now you don't have a zero there, or you don't have 1 times 10 to the minus 7. You're going to form a certain amount based on the first equilibrium. But guess what? These two are equal. These two are equal. So look at the mass action expression. That's shown right here, and that's shown right there. It actually cancels out. Actually cancels out. So your Ka2 is just equal to your carbonate ion concentration. Okay, in this particular case, and that's how you can solve for that right there. Okay, so you'll see that in this example right here where I work with a triprotic system. I'm not going to work it out. I'll just walk you guys through this derivation. So here's our first Ka. Okay, phosphoric acid going to dihydrogen phosphate. Here's our second Ka. Here's our third Ka. Take a look at the 3 reactions because we're going to have to work 3 problems. And the question here is, what is the pH? What is the phosphoric acid concentration? What is the dihydrogen phosphate concentration? What is the biphosphate concentration? And what's the phosphate ion concentration? So let's take a look at the first one. First one's Ka1, and we have this. This actually goes down here. And when we do this, we can do our shortcut, and we get hydronium ion of 2.7 times 10 to the minus 2. Okay, our shortcut is just hydrogen ion is equal to the square root of Ka1 times the concentration of the phosphoric acid, which was 0.100 molar. Try that. You'll see that when you do that, you will get an X value of 2.7 times 10 to the minus 2. And you can take the pH of that easily. Okay, so that's going to be this concentration, hydronium ion concentration, is also equal to our hydrogen H2PO4. Okay, if you subtract that amount from H3PO4, then you get the H3PO4 concentration. If you subtract that amount, 0.10 minus 2.7 times 10 to the minus 2, that's your H3PO4 at equilibrium. And you find out that that amount is not so different than 0.1. Let's take a look at the second concentration. Here, what we have is, see how I use this answer right here for that and for that. And what I'm doing is I'm making assumptions. I'm assuming at the top that 2.7 times 10 to the minus 2 plus x is going to be bigger. Why can I do that? Look at the equilibrium constant. That's 6.2 times 10 to the minus 8. That's going to be very small. So if you're taking a very small number from 2.7 times 10 to the minus 2, it's essentially 2.7 times 10 to the minus 2. And then I'm also making an assumption here that 2.7 minus x is approximately 2.7 times 10 minus 2. So I'm making an assumption that x, because of the equilibrium constant, is so small, it's not going to change this number or this number very much. So they basically cancel, and my x value is just Ka2, which is, according to this problem, my HPO4 minus 2 concentration. Okay. So what are my hydrogen ion concentration total so far? From the first equilibrium, I have 2.7 times 10 to the minus 2. From the second equilibrium, I have 6.2 times 10 to the minus 8. Okay, keep that in mind. Okay, I know I've got only about 5 minutes left, but I want to show you why these problems are not as difficult as you think. Let's take a look at the third equilibrium. Third equilibrium is that, and I apologize that I can't erase that, okay? But what you find out is this concentration right here is your hydrogen ion concentration. And the hydrogen ion concentration is based on the first equilibrium and the second equilibrium. This plus this. But if you add 6.2 times 10 to the minus 8 to 2.7 times 10 to the minus 2, isn't that just 2.7 times 10 to the minus 2? So your hydrogen ion here actually comes from the first equilibrium, which is that right there. And then this chemical right here, okay, is just going to be based on, sorry, not that chemical. This right here is based on that. And that's the answer from the second equilibrium. And if you look at the equilibrium constant for this, that's 10 to the minus 13. So again, you're making simplifying assumptions. You're making simplifying assumptions. But now these two numbers, because they are different, let me clear this. Okay, I apologize for this, because this is a mess, but I want to clear this. Okay, I guess that's a way to clear it. Here, the third equilibrium, you can see that they do not cancel. This answer becomes your initial. This answer becomes your hydrogen. But if you do the math there, then you can calculate the PO4 minus 3 concentration. So the math is not that difficult. The more important thing here is that the hydrogen ion concentration total is equal to the hydrogen ion concentration from the first equilibrium plus the hydrogen ion concentration from the second equilibrium plus the hydrogen ion concentration from the third equilibrium. The third equilibrium hydrogen ion concentration is 10 to the minus 19. The second equilibrium concentration is 10 to the minus 8. And the first equilibrium concentration is 10 to the minus 2. If the question were simply, what is the pH of the solution? You've got your answer in the first equilibrium. You don't have to go through the second and third. Why? Because these are so small, they're not going to contribute very much to the first. Okay, that's what I want you to remember. Now, if these numbers, the second and third equilibrium constant, were somewhat close to the first equilibrium constant, then you have to work it out. But in more times than not, your hydrogen ion concentration from a polyprotic acid comes from the first equilibrium. The problem becomes more difficult if you're asked, and this is true for your activity in lab, if you're asked for the concentrations of all the polyprotic chemicals in solution, in which case you have to actually walk through the problem. But look through this problem, because this will really help you understand where our simplifying assumption works, okay? So in the end, I'm just using 2.7 times 10 to the minus 2 to calculate the pH of the solution, which comes from my first equilibrium, okay? So I'm not going to do this because you guys have a quiz this weekend. I'm going to skip the whole base, because if you can make the argument for acids, you can make the argument for base, except now we're dealing with base and their equilibrium constant is KBs, okay? What I do want you guys to look at, okay, certainly look at the KBs. I want you guys to know this: Ka times the Kb equals Kw. And these are going to be based on conjugate pairs. I mentioned that early on in the phosphoric acid system, but this equation right here shows you that if you know a Ka for an acid, you don't need to know the Kb if you got the Kw. pKa plus pKb equals pKw. That's the other equation. And then the other thing I want to mention is amphoteric system. Amphoteric systems are systems that behave as acids or base. The chemical has to have the ability to give up a hydrogen. That means it's got to have a hydrogen in its formula. And it's also got to have the ability to pick up a hydrogen. That means it's got to have lone pairs, because lone pairs are the structural features that will allow it to gain hydrogen. So if we take a look at bicarbonate or carbonic acid, that's again a classic example. In this particular case, we have carbonic acid, H2CO3, and in the presence of water, it'll give up one hydrogen and form bicarbonate. That's this chemical right here. And then it has a Ka of 4.3 times 10 to the minus 7. The bicarbonate can also give up another hydrogen, and it has a Ka2. We call that Ka2 because it's the second hydrogen that comes off at 5.6 times 10 to the minus 11. But we can also get the reverse, where carbonate, CO3 2 minus, can pick up a hydrogen from water and form bicarbonate, and that has a Kb. Why is it a Kb? Because you're forming hydroxide, okay? Don't get fooled in terms of what equilibrium constant to use. Whenever you form hydronium, it's a Ka. Whenever you form hydroxide, it's a Kb, okay? Because those are, the A and B stands for the molecular event or the chemical event that occurs. A means that the chemical is going to give up a hydrogen. B means it's going to pick up a hydrogen. So keep that in mind. And then bicarbonate can pick up another hydrogen and form carbonic acid, and it has a Kb2. Remember I told you from last time, Ka times Kb equals Kw, but only if they are conjugate pairs. So these right here have the same conjugate pairs, carbonic acid and bicarbonate. If you look at the Ka and the Kb, 4.3 times 10 to the minus 7 and 2.33 times 10 to the minus 8, and you multiply that together, you actually get 1 times 10 to the minus 14, or very close to that, because those are the pairs that have conjugate pairs. Those are the two reactions, forward and backwards, that have common conjugate pairs. And if you take a look at this right here, you'll see that 10 to the minus 11 and 10 to the minus 4 is about 10 to the minus 14. Again, because these have conjugate pairs that are associated with it. So whenever you're trying to figure out, say, a KB because you're given a KA, don't make the mistake of just using any KA. You got to look for the KA that corresponds to the conjugate pair that you're looking for, okay? And that's important, and that's very important. Anyway, we're talking about amphoteric system. And so if you take a look at this right here, you'll see that if I have bicarbonate, it has two paths to go. It can give up a hydrogen and form carbonate ion, or it can pick up a hydrogen and form carbonic acid. Now the question is, again, because this is an amphoteric system, carbonic acid is not amphoteric. It'll only give up hydrogen. Carbonate ions is not amphoteric. It can only pick up a hydrogen in the reverse direction. Carbonic acid will only deliver hydrogen, but bicarbonate can do either one. So that's why it's called amphoteric. The question here is that if you have bicarbonate, and how would you have bicarbonate? You introduce it into solution via sodium bicarbonate. Okay, the sodium is a spectator, and what we'll do chemistry in the solution is the bicarbonate ion, HCO3. Okay, we use bicarbonate as the name. We could also refer to this as hydrogen carbonate, but bicarbonate is the more common name for these things. So you guys are just going to have to get used to it. But the question is that if we put baking soda in water, okay, will that solution have a pH above 7 or pH below 7? Is that solution going to be basic, or is that solution going to be acidic? That's the question, okay? So here's the scheme that bicarbonate can undergo. Remember, we can introduce this. You can't isolate an ion. You have to study the ion from its salt, sodium bicarbonate. That would be a salt because that would be a neutral species, and that could be isolated. And you can get the bicarbonate by putting that in solution because it dissociates. So the question here is that, is this solution acidic or basic? And the key, again, as we talked about in equilibrium, is to look at the equilibrium constant, okay? Bicarbonate can only take this path, that or that. So what you need to do is look at the competing KAs and KB for that path. When hydrogen is released from bicarbonate, it has a tune of 5.6 times 10 to the minus 8, minus 11, I mean. When hydrogen is picked up by bicarbonate, it has a tune of 2.33 times 10 to the minus 8. You can see that 2.33 times 10 to the minus 8 is 3 orders of magnitude bigger than 5.6 times 10 to the minus 11. So this is the preferred path. Again, we're letting equilibrium answer our question, okay? So if that's the preferred path where bicarbonate will form carbonic acid, in the process, it's going to take water, because water is going to be plentiful there, and water is going to give up that hydrogen, because that's the only hydrogen source in your solution, to form hydroxide. And because we're forming hydroxide, that's a KB, and the solution is going to be basic. In fact, you guys should know that whenever we have chemical spills in the lab, we have a big tub of baking soda to neutralize acid, because again, it's going to be basic, but it's not so basic that it's going to cause harm. You guys use baking soda all the time, okay? So this is a good way to figure out whether the solution's acidic or basic, just comparing the Ka and the Kb, okay? So if you take a look at other chemicals out there that will have amphoteric system, and we have to introduce them through their salts. Salts are just an ionic substance where you have a cation and an anion, okay? And in this particular case, the anion is going to have acid-base property. So we have sodium bisulfite. This is bisulfite, HSO3. HSO3 can form SO3 minus 2 or H2SO3. Don't be fooled of H2SO3 as sulfuric acid. Sulfuric acid is H2SO4. That's a strong acid, okay? But sulfurous acid is a weak acid. So again, what you need to do is you need to compare the Kb and the Ka to figure out whether this solution is going to be acidic or basic. So you can do that for all of these. Okay, you can do that for all of these. Which reminds me that experiment 5, for those of you in lab, you guys are going to find out that you guys have a weak acid, and you guys are going to try and find the Ka to identify your acid. And we give you salts for most of those. That's what these are. Okay, that's what these are. These are salts. But if you take a look at sulfurous acid, okay, the Ka that you guys are going to be using is not Ka1, because this right here is Ka1. The Ka that you guys are going to be looking up to compare your experimental result would be Ka2, because that salt will have the, when you do the titration, it's the second hydrogen that's going to be removed, okay? And you can calculate the Ka when you do that experiment. So in this particular case, what you do is you determine a Ka for experiment 5, and then you're going to look in the literature and see which salt or which chemical has near identical Ka values. But you're not going to be using the Ka1 for the salts. You're going to be looking at the Ka2 or the Ka3 if it's triprotic. Anyway, we'll talk about that when we get to lab and we cover that experiment. So these are chemicals with the potential of being, well, these are chemicals that are amphoteric, okay? Let me clear this real quick. So those are the names. And those are what happens when you have a dissolution. Remember, dissolutions when you take a substance and you dissolve it. So the dissolution of sodium bisulfite is going to give you bisulfite ions. Okay, and these chemicals right here are going to have acid-base properties. So one of the questions I generally have in the past is, I give you 42 grams of sodium bicarbonate, 42 grams of baking soda. And the question is, what is the pH of the solution? I also tell you that it's 500 ml, it's dissolved in 500 mils of water. Now, to do this, what you need to do is you need to figure out how many moles you have of HCO3, and then solve the two equilibrium. HCO3 is going to form CO3 minus 2 plus hydroxide, and HCO3 will form, sorry, not hydroxide, hydronium, because it's going to give up the hydrogen. That would be H3O plus, okay? Remember that this comes off and donates the hydrogen to water. This, however, will give you hydroxide, because water will come in and donate its hydrogen to bicarbonate to form H2CO3 plus hydroxide. So you have two problems here, okay? You know the solution is going to be basic, and you know that this concentration is going to be bigger than this concentration. In order to figure out what the pH is, you got to figure out exactly what these concentrations are. And this is how you would do that, okay? This is how you would do that. So it's two problems in one. So here is the equation that you would use to calculate the hydroxide. Remember, it's going to be products over reactant. So this is the products, this is the reactant. And so you just set it up. And this is the equation you would use to solve the hydronium. Again, that would be in this direction. And then what you will see is that the hydroxide is much greater than the hydronium. So take a look at that and see if you can come up with the exact pH for this particular problem. I give you a similar problem. It should be in the, it should come up in the announcement at 5:30. There's a problem set where I give you, I think, HSO3 minus, and I ask you for the pH for that particular solution. So that's due Friday. That'll be a good practice for this whole concept of amphoteric systems. Okay, if you have questions on that, just let me know and I can help you with that. But if you want some points, then there's a question that you will see in the announcement, and that should be released at about 5:30. Okay, so let me switch gears here and talk to you about factors that affect solubility. Okay, it has to do with Le Chatelier's principle. Let's say we have barium fluoride. Again, that's a salt, barium fluoride. And you might not think about barium fluoride in terms of acid-base chemistry, but you got to remember fluoride is the conjugate of HF. And HF is a weak acid. Because it's a weak acid, its conjugate is going to be a base. And because it's a base, it's going to have some chemistry in water. That's why you have to know the 7 strong acids, because if you had like barium chloride, then that's not going to have any acid-base properties, because when that thing dissolves in water, it's going to form chloride ions. And the conjugate of the chloride ions is HCl. And HCl is a strong acid. So HCl, this chemical HCl will not form, because the fact that it's a strong acid means that it wants to dissociate. It wants to stay apart. It's never going to come together to form HCl. On the other hand, fluoride is a weak base, which means that it will pull a hydrogen from water and form HF. Okay, that's why it's important, again, like I said, to remember the 7 strong acid, because then everything else is going to be weak. So if we have fluoride and we want to see whether or not we can increase the solubility of that salt in water, then we can do a little bit of acid-base chemistry. We can see that if we have fluoride, fluoride will react with water and form HF. You know that HF is an acid. So if we can drive this reaction to the right, how can we drive that reaction to the right? By reacting HF or putting acid in the solution so that the hydroxide will react with the acid. If we can drive this reaction to the right, then the above reaction will also be driven to the right. And that means that we can increase the solubility, because this second reaction will consume fluoride. The fluoride is going to be found in that first reaction. According to Le Chatelier's principle, if we start removing the fluoride, then that means that there's a deficit on that side. That means that the reaction has to make up for that deficit. The reaction has to proceed to the right. So what we can do is we can either increase the solubility or decrease the solubility by changing the pH of the solution. Okay. If we make the solution more acidic, then it'll consume the hydroxide. The hydroxide is going to cause this reaction to move in a forward direction. That will increase the solubility. If we make this solution more basic, then it'll cause this chemical to increase. It'll drive this reaction to the left, which means that the fluoride ion in the first equilibrium will go up. According to Le Chatelier's principle, if we have excess chemical, then we gotta try and displace that excess chemical. We have to relieve the system by converting that to something else. That means that that fluoride is going to combine with barium and form more barium fluoride. You see more barium fluoride precipitate out. The solubility will decrease. okay? And that's what's summarized here in this slide. HF is, okay, F minus can be removed further by addition of hydronium, like that. Okay, so we increase the solubility by making the solution acidic. Likewise, we can decrease the solubility by making the solution more basic, just based on what you guys learned already, Le Chatelier's principle. Okay. Here's another question that you might see in the homework. It's a question that I usually ask in some exam questions. And the question might be the following. If you got H2S in water and you form hydronium and HS, which way will the equilibrium lie? Will this equilibrium lie to the right or to the left? And what you have to think about in these reactions is that you have two acids. This is an acid because this is the chemical that's going to give up its hydrogen. Okay. This is a chemical that gives up its hydrogen to form HS. And this is an acid because that's the chemical that gives up its hydrogen to form water. So what you have is two acids that are going to compete against each other. Remember, the role of an acid is to give up its hydrogen. It's going to be the proton donor. Which has a stronger ability to give up its hydrogen, H2S or H3O plus, which is a stronger acid. The stronger acid is going to win out, and it's going to drive the reaction in that reverse direction, in the direction that where it's going to give up its hydrogen. Okay, so what you can do is also look up the Ka for H2S and the Ka for hydronium, and whichever is bigger is going to be the stronger acid. Here's another example. We have this reaction, and it's your job to identify which is the acid on the left and which is the acid on the right. Remember, the acid is the proton donor. So if you take a look at the chemicals on the left, this is the chemical that gives up its hydrogen to form phosphoric acid. So that's your acid on the left part. And this is the chemical that gives up its hydrogen to ammonia to form dihydrogen phosphate. So you're looking at the competition between these two, ammonium and H3PO4. The stronger acid is going to drive the equilibrium either to the left or to the right. Okay, you guys should know that certainly phosphoric acid is a stronger acid than ammonium. So this reaction will actually be driven to the left, and the majority of chemicals in that mixture, because remember that when you have these chemicals and you have it in a beaker of water, you have all of these ions in that beaker of water, and the question is which one is the majority. It's going to be the chemical that is in which the equilibrium is shifted. If the equilibrium is shifting to the left, then the majority chemical is going to be H2PO4 and NH4 plus, okay? Because the job of an acid is to give up its hydrogen. If this is a stronger acid, then it's going to give up its hydrogen to ammonia. That's the proton donor. And what you get is the majority of ammonium and dihydrogen phosphate. You can do that with this as well. Okay, hydrogen bromate and hydrogen bromide. So the question is, which one is the stronger acid? The one before oxygen is going to be the stronger acid. So that means that this reaction is going to be driven to the right, and the majority chemicals are going to be these guys right here. That's not a minus K, that's just a minus. So we can actually figure out which way the reaction is going to be driven, which one's the majority chemical. If we can take all these chemicals and arrange it from strongest acid to the weakest acid, and you can see that right here between hydronium and H2S, hydronium wins out, so the reaction is going to go in that direction. The majority of chemicals in the solution will be H2S and water. Okay, because the reaction is going to go to the left. Between ammonium and phosphoric acid is a stronger acid. So again, the equilibrium is going to shift to the left. The majority of chemical is dihydrogen phosphate and ammonium. between hydrogen phosphbromide and hydrogen bromate. Hydrogen bromate is a stronger acid, and the reaction is going to shift to the right, or it's going to favor the products. And the majority chemical is HBRO3 and BRO4 minus. And finally, the last one is acetic acid. You guys should know this. Okay, it's a common acid, so you should just commit it to memory, versus hydrogen cyanide. Acetic acid is a stronger acid than hydrogen cyanide. Okay, so the reaction is going to favor, it's going to favor the product. The products are going to be the majority chemicals, because acetic acid has a stronger ability to give up its hydrogen. So I just want you to be aware of that, because those are some of the questions that you might see in this chapter, where you're given a reaction and it's going to ask you which is the chemical that is going to be the majority in your solution. You have to look at the competing acids, because those acids are going to compete in terms of donating the hydrogen. The stronger acid will always win out. Okay, the stronger acid will always win out. And you know which is the stronger acid, because you have either the Ka, or you can find it in a table. Okay, here's a problem. And these are typical problem that I usually put in the midterm. I'll give you a salt, I'll give you a chemical, and you need to calculate the pH. You should recognize that this is a strong base. If you know the concentration of this chemical, then the POH is directly obtained based on the hydroxide ion concentration. This chemical is going to form HSO3 minus. That can either form H2SO3 or SO3 minus 2. The question is, which is the majority chemical? That's an amphoteric system, remember? And so you look at the Ka and the Kb. And then this right here, the sodium is a spectator. What you have is phosphate. Phosphate in water will form hydrogen phosphate. So you know it's going to be a basic solution. You know it's going to be a basic solution. Okay, so these are just, you guys should practice this to make sure that you know how to do these calculations. Okay.